Hello guys, my name is IBM and I'm recording February and March 2025 physics papers. I have already recorded these papers but I got a strike, so I had to change different ways. I have to find different ways of re-recording this paper. So I'm going to divide this paper into four parts, and part one, I'll make sure that part one this is going to be part one. Part 1 will have questions from 1 to around 10. I don't want the videos to be very long because I want to give more explanation. So part 1, which quantity is a scalar quantity? Now, if you're a teacher or if you're a student, I want you to notice that in this curriculum in AS, there are only 6 vectors. And if you know the 6 vectors, then the rest are going to be scalars. For example, in kinematics, you have velocity, you have displacement, you have acceleration, acceleration. Those are three in kinematics. Then in dynamics, you have force, or you can also talk about weight because weight is a force. Then you have momentum. That is in dynamics. Then in a topic called force, density, and pressure, of course, apart from force, you have moment because moment is under force, density, and pressure. So you have moment. Of course, we know that impulse is changing momentum, so I can have momentum or impulse here. Moment, or we can also have torque, because torque is another word to mean momentum, moment. So these ones are the 6 vector quantities we talk about in AS physics. That means everything else outside these ones is going to be a scalar. So force is a vector, momentum is a vector, velocity is a vector, so the answer is going to be D. What is the effect of a systematic error on the measurement of a physical quantity? So we know that a systematic error affects measurements in one direction. This one affects measurements in one direction, which means that a measurement or all measurements are either above the expected value or all of them are below the expected value but not above and below at the same time. So a systematic error affects measurements in one direction, either all of them being above the true value or all of them being below the true value but not on both sides at the same time. So unlike a random error, for a random error, it makes values to scatter above and below the true value. This one makes all values to be above the true value. So let's check which options we have here. It limits the precision of the measured value. Of course, precision is how close the measured values are to each other, irrespective of whether they are correct or not. A systematic error does not affect the precision. So precision is actually the range or depends on the range between the values. So systematic errors will make values to be above the true value by a constant amount. That means the systematic error will not affect the range between the values that have been obtained. So this one is not true. It limits the range of values between obtained in repeated measurements. Of course, the range of values relates to the precision. High precision means a narrow range of values. Low precision means a wider range. So this one relates to the first answer, so this is not correct. It results in repeated measurements having different values from each other. Of course, repeated measurements are expected to have, they could be having different values from each other, but if there is a systematic error, the repeated values will deviate from the true value by a constant amount. So this one is not as a result of a systematic error. It can also be as a result of a random error, because a random error, every time you press a stopwatch, for example, you may record a different values of time for 10 oscillations, yet you're using the same stopwatch and we are still timing 10 oscillations. So this is actually a random error. It results in the measured value being different from the correct value. Of course, a systematic error will make the average of the values taken to be above or to be below the true value, which makes the measured value to be different from what is expected from the corrective value or from the true value. So um, a systematic error will have the effect of making the measured value to be different from the corrective value because all values will deviate from the true value by a constant amount. A car is accelerated by a constant resultant force of 300 newtons for 5 seconds. Of course, we know that for resultant force F equals to the mass times the acceleration. The variation with a time of the velocity in centimeters per second of the car is shown. What is the mass? The answer is in kilograms, so we need to find the acceleration in the SI units. So the acceleration A is equal to the change in velocity divided by time. The change in velocity is going to be 150 minus 30. So from 30 to 150, the time is 5. But remember, this was in centimeters per second, so I'll multiply this by 10 to the power of minus 2 to change this to meters per second, then divide by 5 seconds. So the acceleration is going to be 150 minus, so that is 120 divided by 5 times 10 to the power of minus 2, which gives us 0.24. So the acceleration is 0.24 meters per second squared. So what is the mass of the car? So the mass is going to be the resultant force divided by the acceleration. The resultant force is 300 newtons divided by the acceleration, which is 0.24. So this gives us 300 divided by 0.24, which is 1250 kilograms. Of course, to two significant figures, this is 1300. And therefore, the answer is going to be C. An aircraft initially stationary on a runway takes off with a speed of 85 kilometers per hour in a distance of no more than 1.2 kilometers. So it was initially stationary, which means initial velocity is 0. Then this is going to be the takeoff speed, which I will call V. What is the minimum constant acceleration? Because they're talking about a constant acceleration, it means the equations of motion can apply. Equations of motion can apply. So I'll first change this speed to meters per second. So this is going to be 85 times 1000 divided by 3600 to change it to seconds. So this is meters divided by seconds. I'm finding the takeoff speed. So the takeoff speed is 85 times 1000 divided by 3600. So that is 23.61 meters per second. 23.6, is it 61? It is the one which is requiring, so it is 23.61 meters per second. That is the takeoff speed. So since the acceleration is constant, the equations of motion can apply. So I'll use v squared equals to u squared plus 2as. So the takeoff speed is 23.6 squared equals to initial speed, which was 0, then plus 2 times the acceleration times, they said not more than 1.2 kilometers, which is 1.2 times 1000, which is 1200 in meters. So I'm trying to find the acceleration. I'll just press my calculator and just get 23.61. This was 61 squared divided by 2 times 1200. So 23.61 squared divided by 2 times 1200. So that is giving us 0.23. So the acceleration is 0.23 meters per second squared. So the answer is going to be A. An object is fired upwards from horizontal ground. The object has an initial velocity of 20 meters per second at an angle of 45 degrees to the horizontal. Okay, air resistance is negligible. So if air resistance is negligible, then the acceleration is constant, which is going to be the acceleration due to gravity. Which statement describes the speed of the object after it is fired immediately before it reaches the ground? Okay, I'll try to sketch the motion of this here. Because a projectile is in 2 dimensions. So let's sketch this assuming it moves in that direction. So that is in the vertical plane, the horizontal plane. I'll change the color here for us to be able to visualize this. So I'm assuming it is projected at an angle of 45 degrees to the horizontal with an initial speed of 20 meters per second. Of course, if it comes back to the same horizontal position, the same point, it means the speed here is also going to be 20 meters per second. The speed will only change if it continues to fall below the point of projection. But if it lands at the same level, then the speed with which it lands must also be 20 meters per second. However, it is projected at an angle of 45 degrees, which means that it has a component in the horizontal which does not change, and that component would be 20 cos of 45. Even at the highest point, the component in the horizontal again still remains 20 cos of 45. Even when it lands, the component in the horizontal remains 20 cos of 45 because the horizontal velocity does not change. But in the vertical, because the acceleration acts vertically downwards, in the horizontal it remains the same because there is no acceleration in the horizontal. But in the vertical, the acceleration is 9.81 meters per second squared. So the velocity decreases to 0 in the vertical plane. So in the horizontal, it remains that one. At the highest point in the vertical, velocity becomes 0. That means resultant velocity at the highest point is just the velocity in the horizontal direction, which is 20 cos 45, and 20 cos 45 must be less than 20. Let me check. 20 cos of 45. That is 14 point. This is 14 point something. 14.1. So that is 14.1 meters per second. So the velocity at the highest point is just in the horizontal, which is 14.1 meters per second, because velocity in the vertical becomes 0. So that means the velocity in the vertical decreases to 0, and then now it increases back to its original value. Remember, in the vertical, the velocity component in the vertical at the point of projection is 20 sine of 45, which goes on reducing until the highest point. So which statement describes the speed of the object after it is fired until immediately before it reaches the ground? Immediately before it reaches the ground, the speed goes back to its original value, which is 20, because the vertical component goes back to 20 sine 45, but in the opposite direction. The horizontal component remains 20 cos 45 throughout, and the resultant of the two components is still going to be 20 meters per second. So when its speed decreases to a value greater than 0, it can't decrease to a value, it decreases to a value greater than 0, which is very true. In the vertical, it goes to 0, but in the horizontal, it remains 14.1. So it means that if the speed has decreased to 14.1 in general, therefore the answer is most likely going to be this one here. At the highest point, in the vertical, the speed is 0, but in the horizontal, the speed is not 0. It is 20 cos of 45. So The speed at the highest point is not zero unless we only consider motion in the vertical direction. Its speed decreases to a value greater than zero, then increases. Here its speed decreases to a value greater than zero, then increases to 20 meters per second. That one was we say that is true. Its speed decreases to a value greater than zero, which is still true, then increases to a value greater than 20 meters per second. It does not because the folds are the same horizontal point, the same point or the same height. If it goes up to the highest point and falls at a point which is in the same horizontal line with the point of projection, then the speed does not go beyond 20 meters per second. It will only go beyond 20 meters per second if it continues further or below the point of projection. Its speed decreases to zero, then increases to 20 meters per second. We say this only happens in the vertical plane. In the horizontal plane, the component remains constant, which is 20 cos 45. Its speed decreases to zero, then increases to a value less than 20. As long as it falls at the same point, at a point which is on the same horizontal line as the point of projection, then the speed with which it lands is the same. So we are saying that our answer is going to be A. So all the four answers look or seem to be correct, but if you pay much attention, you'll notice that the most appropriate answer is A. Its speed decreases to a value greater than zero, which is 14.1, but then the speed increases back to 20 meters per second if it falls at a point, or if it falls again to the same ground. I'm still emphasizing that the speed will only go beyond 20 meters per second if it falls below the point of projection. That is, if the motion starts from, say, this point and then the body falls up to this point. So it will have fallen below this point of projection. Then the speed will be less than 20 meters per second if the object is projected and lands at a point which is above the point of projection. So the answer is A. What is a statement of the principle of conservation of momentum for an isolated system? We know that for an isolated system, there is no resultant external force. No resultant external force. There will be no resultant external force. And therefore, for an isolated system, the total momentum before collision is the same as total momentum after collision. Or we can say that the total momentum of an isolated system of interacting bodies is always constant. Total momentum of an isolated system of interacting bodies is always constant. So if there is no external force acting on a system, then the momentum is said to be conserved. Whether the collision is elastic or inelastic, momentum is always conserved as long as the system is isolated. Okay, let's see what you have here. Total momentum and total kinetic energy are always conserved. This is not the principle of conservation of momentum. Kinetic energy may not be conserved, but momentum is always conserved as long as the system is isolated. Total momentum is conserved only in elastic collision. That's also not true. Whether the collision is elastic or inelastic, momentum is always conserved as long as the system is closed or the system is isolated. Total momentum is conserved provided that no external forces act. I think this is correct because if there is no external forces acting, then the system is said to be isolated. Therefore, total momentum is going to be conserved. However, if you are stating the principle of conservation of momentum, we say that for an isolated system, total momentum remains constant. Total momentum of each object in the system is the product of mass and velocity. This is just defining linear momentum. It's not the principle of conservation of momentum, so the answer is C. Objects P and Q form an isolated system. Okay, that means momentum is going to be conserved. Object P has mass 6 kilograms and is moving at a speed of 3 meters per second. Object Q has mass 2 kilograms and is moving at a speed of 4.2 meters per second at an angle of 35 degrees to the path of P. So we notice that Q is moving in 2 dimensions, so it has a component in the horizontal where we resolve 4.2 to the horizontal, which will be 4.2, I think that is cos of 45, and then in the vertical, resolving 4.2 in the vertical to be 4.2 sine of 35. Okay. Objects P and Q collide and stick together. So if they stick together, they move with a common velocity. They stick together, therefore they move with a common velocity. I will call that common velocity V. What is the magnitude of the component of the final momentum of the combined objects in the original direction of P? That is just in the horizontal. So we are going to consider momentum in the horizontal. So I'm going to consider only horizontal momentum. So I'll ignore the vertical component, horizontal momentum. So I'm going to conserve horizontal momentum only. Remember, momentum is mass times velocity. So total momentum before should be the same as total momentum after. So total momentum before collision, let's say momentum to the right is positive, momentum to the left is negative. So to the right, it is 6 times 3, that is for P, then plus. For Q, it is, because it is moving to the other side, momentum to the left is going to be negative, so this is going to be 2 times negative minus 4.2 cos of 45. So I can say velocities to the left are negative, velocities to the right are positive. So this should be called total momentum after collision. Because they stick together, the mass combines. So the mass is going to be 6 plus 2, then times the common velocity, which I'm going to call V in the horizontal. So this gives us, that is 18 minus, let me just use my calculator, 18 minus 2 times 4.5, sorry, 2 times 4.2 cos of 35. So this is cos, I don't know why I'm writing 45 instead of 35. That is called a transcription error. So 4.2 cos 4.2 cos 35. This is 35. Okay, so we have 11.1, let me just say 12 is equal to 8 times V. So V equals 2. I can even just divide that by 8. So this is giving me 1.39. What is the magnitude of the component of the final momentum of the combined objects in the original direction? Oh, sorry, we were not finding V. It wasn't necessary to find V, but anyway, V would be 1.39. We want the magnitude of the component of the final momentum of the combined objects. Because momentum is conserved, Total momentum before collision is this. It should be the same as total momentum after collision. So the answer is going to be just 11. Total momentum is just 11 because total momentum before collision is the same as total momentum after collision. Since we want the total momentum when the objects are combined, so I may not even find V because it will be a repetition here, so I don't even need this. I just need total momentum before collision, which is 11.11 kilogram meters per second. Okay, so the answer is 11. An astronaut of mass m in a spacecraft experiences a gravitational force F equaling to mg when stationary on the launch pad. What is the gravitational force on the astronaut when the spacecraft is launched vertically upwards with an acceleration of 0.2 grams? Okay, so let's try to put this in a sketch and see what is really happening. Let's say the astronaut is just standing on the launch pad. So when the astronaut, assuming this is the launch pad, so they have told us that the astronaut has experiences the gravitational force F, which is actually his weight. That is mg. Gravitational force F equals to mg. Of course, this is the same as the force exerted in the upward direction. Remember, the gravitational force is actually the weight. Is actually the weight of the astronaut. So what is the gravitational force on the astronaut when the spacecraft is launched vertically upwards with an acceleration of 0.2 grams? So the acceleration of the launch pad, the acceleration of the spacecraft does not affect the weight of the astronaut at launching because the weight depends on the mass of the astronaut. The weight of the astronaut will depend on the mass of the astronaut and the acceleration due to gravity or the gravitational field strength, which is still which is still g. So the weight is going to depend on the mass and the acceleration due to gravity, which is still g, not the launch acceleration. Therefore, it means that F against the force or the gravitational force is still going to be the same as the weight, which is still going to be just mg. So even if it's launched with even if the spacecraft is launched with a vertical acceleration of 0.2 grams, I mean 0.2 times acceleration due to gravity, this will not affect the weight of the astronaut because the weight will still be depending on the mass of the astronaut and then the acceleration due to gravity caused by the Earth. So this is going to be still B. The diagram shows a child X of mass 20 kilograms and a child Y of mass 15 kilograms seated on a uniform plank. Because the plank is uniform, we know that the weight of a uniform object acts at the midpoint. The plank has a mass of 7 kilograms and has a pivot at its midpoint. So it means the weight of the plank is just acting here, therefore it will not have any moment. The plank is horizontal and in equilibrium, which means the resultant force is 0 and the resultant moment is also 0. So the weight of this one is going to be 20 times gravity. The weight of this one is going to be 15 times gravity. Which statement about the weight of the plank is correct? Because the plank is uniform, its weight acts at the midpoint. For any uniform object, its weight acts at the midpoint or its center of gravity is at the midpoint. And remember, center of gravity is the point at which the entire weight of the object may be considered to act. So the first statement, the weight of the plank can be considered to be acting at its midpoint. For a uniform object, its center of gravity is considered to be at the midpoint, and that means its weight may be considered to be acting at that midpoint. Therefore, without even wasting time, the answer is going to be A, so no calculation is needed here. Lastly, for part 1, an object is fully submerged in a liquid. Fully submerged in a liquid. Okay, if an object is fully submerged in a liquid, the forces acting are its weight. If the object is not moving, there is no drag, there is no viscous drag. But the second force acting is the upthrust. And if the object is fully submerged, the upthrust must be constant because the upthrust depends on how deep, I mean the depth of the object that has been submerged. If the whole object is now fully submerged, then the depth, the height of the object is constant because we know that upthrust is equal to the cross-sectional area times difference in pressure between the top and the bottom of the object, which is cross-sectional area times density times g times this, the depth of the object which has been submerged. If the whole object is submerged, then this one also becomes constant. Everything here becomes constant, which means the upthrust becomes constant. The student determines the ratio upthrust acting on the object over weight of the object. Which single change would double the value of this ratio? Which single change would double the value of this ratio? One, of course, we know that the weight of the object is constant. Weight is constant. Which single change would double the value of this ratio? Remember I said upthrust is difference in pressure. I mean area times difference in pressure, which depends on the depth, because area, density, and G could be constant. So use a different liquid that has twice the density and the same volume as the original liquid. Twice the density and the same volume. Twice the density and the same volume. So if it has twice the density by the same volume, it means the same volume means, of course, this one is the same as area and depth, that is volume, so that is V density times G. So same volume but twice density, it means the upthrust, the new upthrust will be equal to V times twice density then times G. So it means it is going to be twice. So the answer is going to be A. Which single change would double the value of this ratio? So the answer is A. Use a different liquid that has twice the density but the same volume as the original liquid. If we use a different object that has half the volume and same density, it means same density but half the volume, that one will reduce the upthrust by a fraction of 2, or it will half the upthrust. Use a different object, so this one will make the upthrust half of the original. This was twice the upthrust. Use a different object that has twice the density and the same volume as the original object. So if the volume of the object, same volume as the original object, but twice, the other one was same volume as the original liquid. Use different liquid that has twice the density and same volume as the original liquid. Here they are saying use a different object that has twice the density and same volume as the original object. So the upthrust does not depend on the density of the object, it depends on the density of the liquid in which it is submerged. Therefore, this will not actually double the upthrust, because when it has twice the density and same volume, it means the mass has changed, because mass equals density times volume. So you have changed actually the weight. In a nutshell, you have changed the weight. Therefore, it means the ratio is not going to be doubled instead, because you have actually increased the weight. So that there is no way you'll be doubling the upthrust. Use a different object that has twice the volume and the same density. The object has twice the volume and the same density as the original object. So twice the volume, same density also means that the mass has been increased. So you have changed the weight of the object, and therefore you cannot be doubling the value of the upthrust in this case. So in a nutshell, if we use a different liquid that has twice the density and same volume as the original liquid, we have doubled the upthrust, but we have kept the weight the same, therefore we have doubled that ratio. Yet the other factors affect the weight of the object too, therefore, in fact, the others also all increase the weight of the object, therefore, they can, this one increases the weight of the object, this one also increases the weight of the object, therefore, it means the ratio cannot be doubled. So in other words, it just reduces. Okay, so I want part 1 to stop here. See you in part 2, which will be questions from 11 up to 20. Bye bye.